Okay, so today we're going to have last class. I had originally planned to do some new math, but then I thought, hang on, I've got to round up the whole class. So instead of going into how to use an astrolabe, which is interesting, but let's kind of like finish up the course. So remember back at the start of the semester, I was talking about kind of mathematics as a human activity. And I don't know how successful I've been, but hopefully you do see, you have seen that idea. Obvious ways I think you can see it is kind of in the whole idea of influences, like there's contact between different cultures and ideas are transmitted. And we've definitely seen that. We've also seen kind of the importance of kind of new ideas and inventions. So for example, the idea of zero, how how it arose in India, and maybe that's something to do with the culture that was in India, that they were more accepting of ideas like zero and infinity than, for example, the classical Greeks were. We've seen the importance of invention. So, for example, when we started out doing arithmetic, we talked about the dust board and how people did arithmetic with the dust board. And then later on, paper was invented. And kind of that made doing calculations a little bit different. We've also seen how mathematics itself has brought forward inventions and ideas and tools. So for example, we've been really big on trig tables, and we've seen how a lot of mathematical effort was put into creating really accurate trig tables, and then various auxiliary tables. So if you look in the textbook, they talk about all kinds of auxiliary tables that they created. So there's, for example, if I can find it, I can never find things when I want it. Right there. Oh, here we go. So like, for example, tables of corrections for horizontal refraction. So like when the sun goes down, how the light is bent. Tables for afternoon prayer. Tables for the duration of morning and evening twilight. Tables for orienting ventilators. So, like, this is like the air conditioning that went on. So you would have a tower, and you have sort of open, and you have these wet cloths inside, and the idea was to create a circulation to cool the air. And so you want to be able to orient that based upon where the sun was. Tables for the hours of sunrise, the length of day, all these kinds of things, kind of useful things that we use then in society. And then at the same time also, we're getting towards the end, and we're kind of seeing how the importance of instruments are. So a big thing, of course, was the telescope, and this led to a revolution in astronomy, because now they could actually test models more accurately, and this is how the Ptolemaic system was overthrown by the Copernican system. And we had Kepler as well coming along with these three laws, in which was really a really tour de force of data analysis. So Kepler took this mass of observations that were made by Tycho Brahe, which were pre-telescopic observations, but he had masses of them, and he computed through those, and he came up with these 3 laws, not based on any theory, but just based upon observation. And of course, the reason why he was able to do this was because he was able to do computations more efficiently than before. And the reason for this was the invention of logarithms. So he was able to use logarithms to do his calculations. And then after he produced these 3 laws, along comes Newton later with Principia, and he develops a theory about why Kepler's 3 laws might occur. Okay, so it's kind of seeing this push of mathematics being influenced by what happens beforehand and then influencing what happens after. So very much kind of this human activity. So we've been kind of really looking at various mathematical traditions. And so we started off, remember, talking about what we might call early Western, where it include Egypt, Mesopotamia, classical Greece, and the Hellenistic world. And you kind of think, Western? When is Egypt and Mesopotamia in the West? Well, it kind of used to be, right? Because one of the things that the Islamic conquest brought about was it kind of shifted what was the West. Because the West used to be just the kind of Mediterranean Sea, what was around that Mediterranean Sea. And so that was kind of like the center of kind of Western culture as we kind of think about it with the Greeks and the Romans. And we've kind of seen how they were influenced before by Egypt and Mesopotamia. Okay, and then when the Islamic Empire came out and sort of conquered North Africa, that kind of shifted, brought about Europe, right? Because then afterwards, we had people like Charlemagne, king of the Franks, and France and Germany became kind of like powers. And we saw other very strong mathematical traditions, particularly India and China. We didn't spend really as much time on those as they deserved. We could have done a course just on each one of those things. We briefly looked at Korea and Japan, and of course, the main thing that we did in this course was looking at medieval Islam, how it was kind of like this conduit of kind of ideas that came before, and then there was that transmission of ideas afterwards, which is kind of like, I hope, one of the things you take from this course. So when people study history of mathematics, kind of like the big thing, the big topics that they want to study is, well, what were the influences from one mathematical tradition to another mathematical tradition? So, for example, China. So, as I've emphasized before, China had a very strong mathematical culture. They were exceptionally good at solving equations, particularly. The algebra was very good. They had this system of sort of counting boards, and so it was very natural to go from a counting board to look at things to do things which is basically the same as matrix algebra and algebra with polynomials. And that's still kind of not really known as much as we like, how ideas went, particularly mathematical ideas, went between China and other cultures before the 16th century. There's lots of tantalizing possibilities because we see kind of things that are sort of common to all the cultures, like everyone could solve quadratic equations. They kind of knew Pascal's triangle. A lot of them did solved congruences. So there's so we've seen how India was where the decimal system that we kind of use today sort of started. But there's like kind of hints that maybe there was some Chinese influence in that as well. So we've seen the use of the Euclidean algorithm to solve congruences, and that might have come from China as well. They don't really know. So the idea is, it's kind of obvious that maybe there wasn't like a book that went from one culture to another, and so they copied that thing directly. But ideas might have crossed and said, oh, you can use your Euclidean algorithm, and so they maybe knew about that was done there, and maybe they did something similar over there. We've seen, so this Horner's method, we actually kind of saw it a little bit before when we looked at how by arithmetic you compute roots, like we looked at the fifth root of that number, or looking at square roots or cube roots. You can actually apply that to polynomials. You can actually solve polynomial equations by that method. It's known as Horner's method in the West. I think that was early 19th century. I did that. So it's possible that the Islamic method of solving those polynomials numerically, maybe that idea originated in China. There's definitely Islamic influences on China, mainly coming from Persia, which happened during the Tang dynasty, which remember was around 800 as well. And Yuan, I hope I'm pronouncing these right, that's when the Mongols ruled China. And there's definite Indian influences on Chinese development of trigonometry in Chinese. But people would like to know a whole lot more about that. At the end of the 16th century, so whoever did the last bit of China, anyone here did that? There was a Jesuit priest, Matteo Ricci, came to China, and he and his student translated Euclid into Chinese in 1607. And that kind of sort of marks the beginning of the end for indigenous Chinese mathematics. And Chinese mathematics was then sort of globalized and became part of the world of mathematics. Similar thing happened in Japan and Korea, although there, in Japan and Korea, they were strongly influenced by Chinese. So in East Asia, Chinese was kind of like Greek in the Hellenistic world, Sanskrit in India, Arabic in the Islamic world, and Latin in medieval Europe. Sort of Chinese was the scholarly language that was used throughout East Asia. And Korea, so stuff would go from China through Korea into Japan. And so Japan and Korea were kind of heavily Chinese, and they sort of didn't really start new and original sort of indigenous mathematics until the 17th century. So that means that there wasn't that for that long, because then the West came in. So if you know your Japanese history, the shoguns really closed down Japan and tried to limit Western influence until Matthew Perry came along in 1854. But even before that, Japanese mathematics were already aware of what was happening in Europe. And so today, sort of Japan, Korea, and China are kind of like mathematical powerhouses. Like if you go to any university in the world, and there's sure to be someone from Japan, Korea, or China in the faculty there. produce a lot of mathematicians. But it's this world style of mathematics that developed, that was sort of transmitted from Europe. India. So again, that's another fascinating thing. So we've seen how India learned trig from Greek sources, particularly the works of Hipparchus. That sort of came along when Alexander the Great did his trekking along. And we definitely know that Islamic mathematicians learnt Indian trig and arithmetic in the 8th century. We know visits of Sanskrit scholars to Baghdad in around 780. But there's still lots of questions that ask. How did quadratic formula come to India? Did India influence Islamic mathematicians with their work on the quadratic? As I said before, there was Indian trig was in China. We've got evidence of that. Really interesting is the in India in the 16th century, in southern India, they developed the power series for various trigonometric functions. And so it's an unknown question about, did those trig series then go to Europe? Because like the Jesuits were in India in that time. And so they quite easily had transmitted those ideas to Europe, because around 1600 onwards is when sort of power series really started to get going in Europe. We know Newton developed power series, so he probably wasn't influenced by India, because a lot of his work is fairly original, because he did it when he was so young. You know, he was like 20 or whatever when he was sent home from Cambridge because the university closed because of the plague. And so when he went home, he invented calculus and you know, came up with an optical theory of light, you know, just in his off spare time as a kid bored at home. So that's, when you go home, that's what you guys are going to do. You've got to do something amazing. But in other parts of Europe, other people also kind of develop ideas about power series. And so is there any influence from these Indian power series to those mathematicians in Europe? That's kind of like an unknown question, and people are interested in that. So we've been looking at Islamic mathematics, medieval Islamic mathematics. And so, unfortunately, by the 15th century, the Islamic scientific culture went into decline. There's kind of lots of reasons for this, but the main reason is like the Islamic states, various Islamic states had sort of hunkered down in some kind of cultural bunker. So there was a lot of fighting between those states. There was a split between the Sunni and Shia states, and so there was a big demand for orthodoxy, and so this really cut down on kind of scientific exploration. It was kind of really frowned upon. Whereas in Europe, I kind of showed you some problems about how in around the year 1000, you looked at the kind of problems that European mathematicians were looking at, and they were, you know, so basic, you know, they had lots of wrong ideas. But by the 12th century, serious mathematics had sort of kick-started. And this was thanks to those translators who translated works from Arabic to Latin. key to that was Al-Khwarizmi, who's kind of been a sort of like a hero of this class. We've seen how he really took the Indian ideas of the numbers and really kind of developed an arithmetic. And then he's the person who followed him, Abu Kamel, right? Basically Fibonacci, who was an important importer of Islamic mathematical ideas into Europe. His book is basically a translation of Abu Kamel's book. So we see that it happens at that time, and so they miss out on the guy that we know was kind of like the big algebraic guy in Islamic, with Al-Samawal. Remember, he was the guy who kind of completed the arithmetization of algebra, and so that we could do things like divide polynomials, etc. He wasn't translated into Latin because he came kind of just a little bit after that great transmission of ideas. And so basically Al-Samawal's ideas, he thought of them first, but they had to be sort of rediscovered by European mathematicians. But that was okay because they had this great influx of ideas, and then they went to that. Other kind of important things was, so we haven't talked that much about sort of other geometries, but really a key work was Al-Tusi. He worked on the parallel postulate. So remember, there was this whole idea that there was a parallel postulate in Euclid, and people were kind of worried about that because they thought, well, it looks like that should be a theorem and not an axiom. So he worked on that. His work was published in Rome, 1594, and definitely people, John Wallis and Gilmero, Saccheri, worked out. Saccheri is very important. He was like in the 1700s. He wrote a book which was called something like Euclid without imperfections, or something like that. And so in it, he took the idea, well, what happens if we remove that parallel postulate? And he came up with, so there's two ways you can negate the parallel postulate, right? And so that is, in one way, let's say in geometry A, so one way to put the parallel postulate says if you have a straight line and you have a point not on the straight line, then there is a unique line that goes through that point which does not intersect that line there. I think that's called Playfair's axiom. It's like that version of the parallel postulate. So in geometry A, you say there is no such line that does that. And in geometry B, you say there's more than one line. Okay, and Saccheri said, well, these things are ridiculous. So therefore we don't need the parallel postulate. Therefore, Euclid is free of imperfections. Unfortunately, he'd actually discovered two new geometries and he hadn't realized it. So this is spherical geometry, which is kind of weird because we've just been studying spherical trig, and so they knew that this was, but it's kind of weird that they just didn't think of it as a separate geometry. And this is hyperbolic geometry. And so eventually, in the early 19th century, Bolyai, Lobachevsky, and Gauss got together and basically invented this geometry. But that's a story for the sequel to this class. We've seen how we've seen trig in both plane and spherical form. We saw how that was important in the Islamic Empire, and that was translated into Latin in the 12th century. And those ideas spread into Europe and were taken up. And so we know that that kind of trig is important for things like astronomy, geography, navigation, for example, which were all things that Renaissance Europe really developed kind of well. But even with all these things, that's still, if you go to a place that you go to a PhD program in history of mathematics and science, that's a big kind of area. It is how much of medieval and Renaissance math in Europe was influenced by Islamic math, either directly or indirectly. So we've already seen lots of tantalizing evidence that there was a lot of influence. So we're in 1600. And so how are things different? Well, math is still rhetorical. So, so this is coming towards, this is what, around 1540 or something. So we've seen Tartaglia did his solution for the cubic. And so unlike us, he had to write his solution as a poem. Okay, so here, when the cube and the things together are equal to some discrete number. So not exactly Shakespeare, but you can see like x cubed plus p things. It's a cube is x cubed. Things would be something like px equal to q. Okay, and then you give a little poem about how you go about solving that. So you follow those instructions. It's kind of like, it's not a formula, it's a recipe, right, about how you go finding a solution. And then here in the second of these acts, when the cube remains alone, well, we know what's happening here, right? Because here it's x cubed plus px equals q. The cube is alone, so this is x cubed equals px plus q. So again, like we've seen before, we prefer things to be positive. So in this case here, he's breaking it into different cases, depending upon whether it's x cubed plus px equals q, x cubed equals px plus q, or what's the other one? Px x cubed plus q, and so you go to these. Yeah, and the third of these calculations of ours is solved with the second if you take good care. And of course, since it's a poem, it has to end with these things I found, and not with sluggish steps in the year 1504 and 30, with foundations strong and sturdy in the city girdled by the sea. I just don't write math textbooks like that anymore. So it's still rhetorical, and the way that there was math controversies was different back then, right? Because so back then they used to have math duels, where the thing was you would challenge another mathematician, and then you would give them 30 problems, and they would give you 30 problems, and then you would solve them, and then you'd have a referee, and then whoever won sort of won the prize. So that's interesting. So these are the kinds of problems that Ferrari sent Tartaglia. So if you remember the video about that, there was this big dispute about the cubic because someone had solved first, had one case, Tartaglia came along and solved it. Cardano came along and begged Tartaglia for the solution. Tartaglia told him on the condition that he'd not publish it, right? Because he wanted to be able to win all these math contests himself, because he could just give these cubic problems and solve it. He was on a big money earner then. But Cardano then published it in a book. And Ferrari was a student of Cardano, and so they had this big fight. And so here are some examples of some problems that were sent. Divide 8 into 2 parts such that a product multiplied by the difference comes to as much as possible, proving everything. And then 22 is some sort of analysis of some work of Plato. 23 is a word problem, which basically means solving these 2 equations. I found question 30 really interesting. Is unity a number or not? Okay. Tartaglia's answer was interesting because he took kind of like the traditional Greek view that 1 is not a number, but it's like a potential number because it's the thing that makes up other numbers. So here is some solutions of Tartaglia. I like his solution to problem 17th problem, where he does the answer and says, and this is the fruit of our tree with which you thought to make war on me, but you failed in that intention. So it's kind of like really bitter things. And then Ferrari kind of criticizes one solution, solution to the 17th problem. So he says, because Tartaglia just gave the solution, and Ferrari complains, proving everything, but you, just like a forger, not only in obscure things, but also in open and public things, omit when reporting my words, the part that matters, and which you did not dare to ignore, namely those 2 words, proving everything. And then having already misused the thing in your way, you decide to simply divide 8 into 2 parts, which I do not wish to tell you whether they are correct ones or not. But I will tell you that in not proving that which my problem requires, you are still leaving it unsolved, and so you show yourself to be that man of integrity and honor that I meant in my last letter. Really kind of pulling thing. And then as for the 22nd, so remember the 22nd was the one about interpreting some passage of Plato. He says, you say it's not a question for a mathematician. And then he goes on, if by a mathematician you mean someone like you, that is someone who spends the whole time on roots, fifth powers, cubes, and other trifles, then you are quite right. And I promise you that if it were up to me to reward you, taking the example from the custom Alexander, I would load you up so much with roots and radishes that you would never eat anything else in your life. But if by a mathematician you mean a man expert in arithmetic, geometry, astrology, and music, and all the other arts that depend on these ones, as were all the ancient mathematicians, and he sort of goes on, and he says, I will tell you candidly that this is not a subject for you, and so interpreting only very clumsily and some lines on purpose into Italian, you will pass along, leaving the problem unsolved. So it's interesting to get these kind of things. They were kind of violent in Renaissance Italy. Like one of these guys, I forget which one, poisoned someone else, and someone else was in knife fights, and Tartaglia, his name being in Italian, it's like his nickname means stammerer. So he had this speech defect. So they kind of made fun of him. So his name was based upon the fact that he was a stutterer. And he was a stutterer because he got hit by a sword in his mouth, and he's got his mouth cut open. And so he couldn't speak very well afterwards. And he always wore this big beard afterwards to hide his scars. So I'm glad I wasn't around in those days. Oh, yes. Okay. So going back to some history. So we can ask the question. So we've kind of seen how the Islamic world has stagnated. So we can ask the question is why kind of was Europe kind of like then the powerhouse that it sort of became. So kind of if you look at Islam, if you look at China, we've seen how Chinese mathematics was really strong. But again, there's things that happened in the history there. So I think with the Ming dynasty and going on to the Qing dynasty, they became very isolationists. And they closed up shop. And again, there was a great emphasis on orthodoxy. And this, around kind of like 1500, this kind of stopped the really inventive flow of things that were happening in China beforehand, especially in the great dynasties like the Tang dynasty and I think it's the Song dynasty that came out afterwards. And India kind of never really had a chance because if you compare India and China, China was mainly unified. There were brief periods when they were kind of like warring states, where there was kind of like a lot of unrest, but the Chinese sort of had this basic goal that China should be united, should be one. And so for most of its history, it sort of like became one empire. Whereas India was always continually in that warring states period. There was, except for one brief time, I can't remember when Ashoka was, I think it's maybe around 600, there was a unified India, but for most of the time, India was this whole bunch of warring states that were fighting each other. And so eventually the British came on, and that was one of the reasons why they were able to take over India and not being able to take over China. So what happened in Europe was they had like an economic revolution. So in the Middle Ages, if you were a merchant, so what you would do was, so backing up a little bit, for a long time, the two major economic powers in the world were India and China. And the trade with India and China was an important economic force in the world. And so you've all heard of the Silk Road, for example. And that went through the Islamic Empire. So they got rich based on the trade between Europe and India and China, basically. And so what would happen would be in the Middle Ages, you didn't really need to do any math, right, to be a merchant. So what you would do is you would be a solitary merchant, you'd get a ship, you'd go somewhere to the east or something like that. You bought some goods that you thought that people wanted, you took them back home and you sold them and you made a profit. And that's how you went. But the Renaissance kind of changed that. For example, there were things like new shipbuilding, better ships, ship lanes became safer. A lot of this has to do with the Crusades and that. And so a lot of merchants sort of stayed at home, and they would kind of send out agents, and they would arrange for shipping. You'd make deals between each other. And so you had the formation of basically what are international trading companies. And once you had that, you needed more sophisticated mathematics because you had to deal with that. So financial math became a real thing there. So you had things like letters of credit, bills of exchange, promissory notes. You had to worry about interest rates, do interest calculations. You had to worry about exchange rates, all kinds of things. So the thing that made all this possible was double entry bookkeeping, which was kind of invented in Italy by Luca Pacioli sometime in the 15th century. So because instead of merchants having kind of like a discrete event where you would go get a shipload of goods, come back and make money, you now kind of had a more continuous flow of goods. And so you had to be aware of what the financial situation was, all kinds of things. And this all happened in like the 14th, 15th century. It happened first in Italy. And then those ideas got exported to the rest of Europe, particularly Antwerp was kind of like a big financial center. And then London sort of took over from Antwerp in around 1600. And then London ever since has been kind of like one of the financial capitals of the world ever since then. Oops. I think that's supposed to be 1549. I want to finish off by just looking at a couple of people who were kind of really important. So the Frenchman Viète, so he's right at the end of the time period we're looking at, and he's really a key person in sort of like looking at a sort of modern way of doing algebra. So he developed a theory of equations. And so remember, we have algebra where you look for a solution to some problem, but he did like kind of like a detailed, he came up with a theory of how the structure of these equations. And he came up with three kinds of analysis. I don't know how to pronounce zetetic analysis, by which you have a problem, you have a word problem, and you turn it into an equation. You have an equation with unknowns and knowns. Okay? Heuristic analysis, that's where you prove a theorem by doing some kind of symbolic manipulation. And exegetics is where you take your equation that you've found and you come up with a value for the unknown. And so if you think about, look at it, this is basically how we use algebra now. Okay? And to solve these problems, you needed better symbolism. And that's one of the things that you would have seen in watching the talks that were given by your fellow students, like the plus sign, the minus sign, the equal sign, the symbol for root. Viète brought up the idea of using letters for unknowns. So I think he would use like vowels for unknowns and consonants for knowns or something like that. So he's a really interesting mathematician. My favorite story about him was that the King of Spain complained to the Pope. Viète was a Frenchman, right? Worked for the French king. So the King of Spain complained to the Pope that Viète must be a witch because he was able to break all the Spanish codes. And the Pope didn't say anything because the Vatican code breakers had already broken the King of Spain's codes as well. So, and the other interesting person from around 1600 was Stevin. And so we know him today as the person who kind of introduced the idea of the decimal point, but that's, well, we know that the decimal point was invented earlier in everything, but the key thing that he came up with was the idea of what is really now the modern notion of number. And so, for example, he said unity is a number. So 1 is a number. And any quantity, including the unit, can be divided continuously. So this is kind of the idea of a decimal fraction. So that you can take a number, you can cut it up, and you can get finer and finer, and you get decimal fractions. So we just think, so he didn't make this distinction between commensurables and incommensurables that we saw beforehand, right? So we all remember how when the Greeks proved things, they would prove things for commensurables, and then they would prove things for incommensurables. And so here is an argument from here. The root of 8 is part of its square 8. Therefore, square root of 8 is of the same matter that is 8. But the matter of 8 is number. Therefore, the matter of square root of 8 is number. And of consequence, square root of 8 is a number. So you didn't have to worry about incommensurables being a different kind of thing from the commensurable. They're the same kind of thing. It's just a number. Hence, we can represent square root of 8 to any acris desired, just as it is enabled 1 to represent 8 itself. So we can take square root of 8 and we can start writing out it as a decimal fraction, and we can write it out as accurately as possible. And this is kind of how we kind of see numbers today. Okay, so we're at 1600, and so the course ends then. And so when I pick up History of Math 2, the thing that I use then to center the course. So in this course, I use Islamic mathematics. In History of Math 2, what I do is calculus. It's kind of like the backbone of the course. Anyway, that's it. I will put out the last assignment, and that will be due on Monday, I'm thinking, although if you really wanted a day or two, you can, but of course you can't do it too long, right, because we're coming up to the end of the semester. I'm going to try and get everything graded by trying to get it like a week before. So basically, I'm trying to get them all done a week before the last assignment is due. So I'm going to try and get all assignments in by that Monday. And see if I'm later, then maybe I'll push that deadline back. So because I know that some of you are going to think about, oh, do I need to do this assignment or not? So I'll try and get and help you with that by getting the other grades in as soon as possible. Any questions? Okay. Thank you. How's everyone going? Is it as stressful as could be, or just normal amount of stress?
I'm just ready to go home.
Ready to go home. Yeah.
I've been home all semester, so I'm like, just my family.
Yeah.